By talking about the trouble with triples. So at some point you begin with a single triple. And triples, you might recall, are tiny, adorable, fuzzy animals that have the property that once every hour that one triple will split into two triples. After another hour, those two triples will each split and you will have four triples. After another hour, all of those triples will split and you will have 8 triples, I guess? I lost count. Let's think about how quickly this number of triples grows. So you start with one triple. At time 0, you have one triple. After an hour, you have 2. After 2 hours, you have 4. After 3 hours, you have 8 triples. After 4 hours, you have 16 triples. After 5 hours, you have 2. After 6 hours, you have 64. After 7 hours, you have 128. After 8 hours, you have 256. Is there some sort of general formula that maybe you're seeing here that tells you how to get how many triples you have after some number of hours? What formula do you see? Well, idea.
Just multiply it by 2 every hour.
Yeah, multiply the number by 2 every hour. So to get n hours, I guess you multiply by 2 n times. So the number of triples after n full hours is n times dot 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 dot. Nope, 2 times 2 times dot 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 times 2 n times. And because that's kind of ugly to write down, especially if you want to ask a computer to compute that, because you obviously do if you look at the next example, you need a shorthand that is denoted 2 to the n. So let's see, after 2 days and 1 hour, that is after 49 hours, how many triples will there be?
2 to the 49th.
2 to the 49th. And I mean, that's an answer. That's a perfect answer. But maybe I care about how big that quantity is. And I had intended to have the computer up and running so I could plug it into a computer. But go ahead and grab a machine, if you have such a thing. I'll begin the process of getting this one. So, how big is it?
5.63 times 10 to the 14.
That is pretty close to 5.63 times 10 to the 14. And that's the right way to write. That's the right way to write that number. Was that up there while I was guessing my password incorrectly the whole time? Okay. I guess you guys can now deduce how many characters are in my password. I think it's long enough that it's still secure. Nice. So, there's a general idea of exponentials, and maybe you notice that 49 isn't that big a number, but 2 to the 49th is quite a big number. So exponentials tend to grow really quickly. So let's talk about what exponentials mean. So if I give you any base b and a whole number n, then b to the n just means exactly what we wrote before. Take b times b times b n times. So 5 to the 6th is just 1, 2, 3, 4, 5, 6. Oh, 5. Fair enough? What if I raise a number to a negative power? What should b to the, well, let's do an example. What should 2 to the negative 3 mean? Yeah.
It's going to be 1 over 2 to raise the power.
Yeah, it should be something like that. Right, so if 2 to the positive 3 means multiply 2 by itself 3 times, maybe 2 to the negative 3 should mean divide by 2. 3 times. So 2 to the negative 3 is 1 over 2 times 1 over 2 times 1 over 2. And you could write that as 1 over 2 to the 3. Right, that's 1 over 2 times 2 times 2. Or you could write that, if you wanted to, as 1 over 2 to the 3, whichever you prefer. So, in general, b to the negative n is 1 over b to the n, or is 1 over b to the n. Both of those are the same. People feel pretty happy? So, I guess that tells you how to evaluate an exponential where the exponent is every integer, but, well, just almost. There are positive numbers and there are negative numbers, and there's one other type of number, right? 0? So if 2 to the n should mean like take 2 and multiply by it n times, then what should it mean to, so 2 to the 0 should be like take 2 and don't multiply by it at all. So it turns out the right convention is just to say that that is 1. And that makes some sense, right? If you take 2 and multiply 1 by it, that should give you 2 to the 1, and indeed it does. So b to the 0 will always set it to be 1. Some goofiness will happen if you try to evaluate 0 to the 0. So we just won't allow that. That is forbidden. Rational powers. If p over q is a rational number, well, let's try to make sense of b to the p over q by starting with, let's raise things to the 1/2 power. So, right, 5 squared, that should be like 5 times 5. Raising something to the 1/2 power should be somehow like opposite of squaring it. So what do you think 5 to the 1/2 should be? Square root of 5. That should be like the opposite of squaring. What if I put anything in that denominator? What should 5 to the 1 over q mean?
Q root of 5.
Like q through root of 5. So if I raise something to the p over q, maybe here's a good way to think of it. That should be like take 5, raise it to the pth power, and then raise that to the 1 over qth power. So that'll be 5 to the p, then take the q through root.
Just lighten it up a little bit.
Yeah, and probably also write more legibly. And that's the same thing as the q through root of 5, then raise that to the pth power. And that's how we'll define b to the p over q in general. B to the p over q, I will always define to be b to the p raised to the 1 over q, or b, which is b, the q through root of b to the p, or take the q through root of b and then raise that to the pth power. But you'll notice I'm taking like a square root right there. Well, I might be taking square root of q as 2. In order to avoid the demons that will appear if you try to take square roots of negatives, I'll just demand that that b be positive. So in general, when I talk about exponential functions, I won't let you talk about like 0 to the n as an exponential function, and I won't let you talk about negative 5 to the n. So with these in mind, let's try to just say some things. What should 2 to the third power mean?
2 times 2 times 2 times 2.
It'll be 2 times 2 times 2, and I mean, you already know what that is. What is that? What should 8 to the 5 over 3 mean? It would be the cube root of 8 to the 5th. And let's see if we can simplify that. Do you know the cube root of 8?
2.
2, because 8 is a perfect cube, so you can take its cube root easily. That's 2 to the 5th, and I guess we already know what 2 to the 5th is. It's in like that table on the top of the page. I think that's 42. Four to the negative 3 should mean, well, 1 over 4 times 4 times 4, which I think is the same as 1 over 64. Well, what about 10 to the 3/5? What should that mean? It'll be the 5th root of 10, and then you cube it. Or it'll be 10 cubed, but then you take the 5th root of it. And of course, like, that's suddenly something that you can't just compute by hand. I don't know the 5th root of 10. The 5th root of 10 is some irrational number. If you want to actually compute the thing, I think today is a good day to demo the following. Have I showed off the Google calculator in class?
Google calculator?
Yeah.
Oh.
I know it's silly to do a Google search for Google, but I guess I just did that. So if I raise 10 to the 3 over 5, Google can do basic calculations if you just type into the search bar. Sometimes it'll betray you if you type in something sufficiently complicated. It'll decide, oh, you meant to search for that. And then it'll give you garbage. Anyway, that's a useful thing to know if you need to do simple computations. You have a machine. So there's no loading time for that. So what do you think? Well, 3 to the 1.4, well, 3 to the 3.14. 3.14 is like, what does a decimal mean? That means exactly 314 divided by 100. So if you wanted to compute that, one way to do it would be, well, take the 100th root of 3 and then raise it to the 314. But of course, you wouldn't do it that way, because if you took the 100th root of 3 using a machine, you would introduce lots of rounding error, probably. And then you raise that to the 314th power, that rounding error would compound. And so you would wind up with a less than trustworthy result. So really what a computer does is there's what's called a Taylor series approximation for exponential functions. That's what a machine will actually use. But that's, if you like, a sales pitch for material from calculus. So if you wanted to actually compute this, we won't compute many exponentials by hand. But of course, a machine can. In fact, what do you think that like 3 to the pi should mean? Well, that's strange, all right? Pi is not even rational, so we can't use the rules that we talked about. It's this non-terminating decimal, so you can't write it as a fraction. And one way to make sense of it is just take like rational numbers that are really close to pi, and those will approximate it. But that's maybe getting just to the peak of how sophisticated I want this class to get. So let's not worry about that. Let's think about graphing the thing. And let's graph it by doing the thing that we know how to do for graphing. Let's try to evaluate at some points. Let's try to sketch a graph of 2 to the power x. And so there are some numbers that I can evaluate 2 to the x at easily, right? If I plug in whole numbers, it's easy enough. What's 2 to the power 0? 1. Anything to the power 0 is 1. Any positive number to the power 0 is 1. So that means the graph of 2 to the x needs to go through 0, 1. What is 2 to the power 1? 2. 2 to the 2 is 4. 2 to the 3 is 8. 2 to the 8, 2 to the 4 is 16. Nice. So it looks like the points on this graph as you go from left to right are getting really high up. The y values are growing pretty quickly. If I went one further to the right, I would be off the page. Let's go to the left. What's 2 to the power negative 1? 1 half. Which? Well, I can kind of draw. That's like about there, about half as tall as 1. What's 2 to the power 1/4? What's 2 to the power negative 2? 1/4. 2 to the power negative 3 is 1/8, 1/16. Those are getting close enough to the x-axis that I can't really tell that they're not on the x-axis at the scale that I can draw. Do you think that's enough information that we can sketch a pretty reliable picture of this graph? The graph of 2 to the x, I mean, assuming it doesn't do anything weird at non-integer points, looks something like this. In fact, do you think any exponential that I try to draw will be pretty similar to that? Qualitatively, anyway. And it'll have some precise quantitative things in common. So let's try to deduce some rules about exponentials. Because right, it's nice when you describe a function to have some algebra that you can do with the function. If you want to like solve equations that involve exponentials, you got to be able to do algebra with them. And let's do some algebra. Let's try to compute 2 to the 5th times 2 cubed. And instead of getting like an actual number at the end, let's try to get an idea instead. What does 2 to the 5th mean?
It's 2 5 times.
It's 2 5 times. So that's, yeah, 2 times 2 times 2 times 2 times 2, because there's 2 to the 5th. What is 2 cubed? It's 2 multiplied by itself 3 times. Hey, wait, is that just like 2 multiplied by itself some number of times? In fact, it looks like it's 2 to the 8th. But maybe more precisely, more relevant to our intuition, that's 2 to the 5 plus 3. I see 2 written down 5 times and then 2 written down 3 times. Let's just see if that intuition holds up. What do you think 4 to the 7 times 4 squared should be? 4 to the 9th? In general, if you have any positive base, and any numbers x and y, b to the x times b to the y is b to the x plus y. And I guess like you're definitely convinced of that if the exponents are both like whole numbers. But the same rule holds even if you evaluate at fractions or at irrationals. So let's make some use out of that. Let's see what that can tell us. Let's compute 2 to the 3 halves times 2 to the 5 halves. And maybe it's remarkable, 2 to the 3 halves isn't actually something that I can compute on the nose as like a whole number. It would require me to take the square root of 2, which maybe you know is like, I think it's 1.4 and some change. But that's not exact. Let's try to compute it using this rule. So 2 to the 3 halves times 3 to the 5 halves. So that's a base to a power times a base to a power. And the bases are the same, so I can just add the powers. This is the same thing. I said 2 that whole time, didn't I? But 3 is actually what's written down. So that'll be 3 to the 3 halves plus 5 halves. And let's just try to simplify that down. What's 3 halves plus 5 halves? 8 halves. And as you said, that's 4. Nice. And now is 3 to the 4 something that you can just write down? Yeah, and 4 isn't even that big, so I bet we can even just compute what it is by like some clever grouping. 81. It will indeed be 81. Maybe just for the sake of intuition, I'll show one intermediate step, because, I mean, you probably just did that in your head. Maybe you did. But maybe you did it by grouping. You said, well, I know what 3 times 3 is. I know what 3 times 3 is. And 9 times 9 is like one of the numbers that's in like the multiplication table that they make everyone memorize. Nice. Similarly, let's try to compute 2 to the 5 times 3. And let's not worry about getting down like a number. Let's just simplify that. Well, no, I want to develop. So let's not get down to a single number. Let's just think about what 2 to the 5 to the 3 means. So what does it mean to raise something to the third power?
Multiply 3 times.
Multiply it by itself 3 times. So that'll be, I'll try to do some color coding here. 2 to the 5th will be green. 2 to the 5th times 2 to the 5th times 2 to the 5th. But let's see, is 2 to the 5th something that you just know what it is? What does 2 to the 5th mean? Well, on the one hand, yeah, it's 42, but I want to like not get a number because I don't want, like I don't care what this number is, I want to build up some intuition for a formula. But it's 2 times 2 5 times. So that means I can expand out each of these 2 to the 5ths as 2 times 2 times 2 times 2 times 2. That's 5 of them, right? Times 2 times 2 times 2 times 2 times 2 times 2 times 2, 3, 4, 5. How many 2's did I just multiply by itself? 15. And notice that's like 3 groups of 5. I mean, that's exactly what multiplication means. It's 2 to the 15th because it's 2 to the 3 times 5. Or maybe you want to say it's 2 to the 5 times 3, but that's the same as 2 to the 3 times 5. Who cares? So for any positive base and any numbers x and y, b to the x to the y is b to the x times y. Yeah. Maybe I should even zoom out a little bit so I don't have to do that as much. Is that zoom still okay? It's still visible from the back? Okay, and now the whole page is in frame, I hope. Let's try to do that, use that to do some things. Let's compute 3 to the 9 halves raised to the 2 thirds. Is that an exponential of an exponential? Yeah, so that means I can use exactly this rule. B to the x to the y is b to the x times y. So that'll be 3, because 3 is the base, to the x to the 9 halves times 2 thirds. The stuff in that exponent, does it simplify at all? Yeah, I think so. Like the halves will cancel, and then you'll have 9 over 3, which is 3, I think. Well, hey, that's even like a number that's reasonable to compute. That's 3 times 3 times 3, also known as 27? Oh, not 2 to the 7th. 27. Does that seem okay? I mean, let's keep on tracking. Let's use these ideas to do some stuff. So, well, wait. So that means that we just noticed one interesting fact. 27 is 3 cubed. That's because that's how you just computed that. Let's just hold on to that fact. Do you think we could use that to compute 27 to the power 2 thirds? I bet, because we could replace 27 with something that 27 is equal to. 27 is 3 to the power 3. Yeah, switch color again. So that'll be 3 to the 3, because that's 27. And then that raised to the 2 over 3. Oh, well, hey. That's an exponential of an exponential, so I can multiply the exponents. That's the same thing as 3 to the 3 times 2 over 3, which is 9. People feel pretty good about that? Maybe I'll say that we could have done this already using just the definitions. Because 27 to the 2 over 3, well, that should be the cube root of 27, and then you square it. But you know what the cube root of 27 is, because it's a perfect cube. Any questions so far? So now that we've developed some algebraic rules, that means that we can try to use these rules to maybe solve some equations. Let's try to do that. Let's try to solve the equation 4 to the x is equal to 32 by using some of these ideas. And at a glance, like, it doesn't seem so easy. But how about this? That graph that we see of 2 to the x up on the top of your page, maybe not on point, but the top of your page. What word would you use to describe that function? What words? What are some properties you see? Does it pass the horizontal line test? Yeah. So here's one fact. Exponentials are 1 to 1. Any exponential equation has at most one solution. In fact, 2 to the x equals any number has at most one solution. So maybe we can represent everything here in terms of powers of 2 and see what we can get from there. Is 4 a power of 2?
Yeah, 2 squared.
It's 2 squared. So this will become 2 to the 2 to the x is equal to, is 32 a power of 2? Yeah, I mean, it shows up on the previous page on that top table, so you know it's a power of 2. Which power of 2 is it?
6.
2 to the 6. Is it really 2 to the 6? Why do I want it to be 2 to the 5th? I want it to be 2 to the 5th. Inside it'll be 2 times 2 is 4 times 2 is 8 times 2 is 16 times 2 is 42. Yeah, so I think it's 2 to the 5th. Nice. So let's look at the left-hand side. 2 to the 2 to the x. How could I rewrite that? Yeah.
It'd be 2 to the 2 times x.
2 to the 2 times x. Aha. Do I see 2 different numbers now inside of an exponential, both giving the same output? But 2 to the x 220 power, that's a one-to-one function. So the only way 2 to the blah can be equal to 2 to the blah is if the two blahs are the same. So the only way 2 to the 2x is equal to 2 to the 5th is if 2x equals 5. So if you like, what I'm using there is that exponentials are undoable. You can undo an exponential. And that's an easy equation to solve, right? What's the solution to that? 5 halves? So apparently the solution to 4 to the x is equal to 32 is x equals 5 halves. Do you think we should like check that? We certainly can check it. Four raised to the 5 over 2, or 2.5 if you prefer. Yeah. Machine says it's 32, and we could compute it by hand, but we have a machine, so we can use that. Similarly, do you think you can now solve on your own 9 to the x is equal to 27? People want me to keep talking through that computation? All right. Solve it. Compare your answers. People are doing that, maybe I'll ask this question again. Does anyone not have a review for midterm 1? Okay, good. Oh, well maybe I'll also do this. that calls for a lethal plot. Josiah Siebel. You are not here 5 minutes early when your name was called. Garrett Albee. Logan Falk. Nope, sorry. Rose. You are getting released now. No, you're good. Ryan Kearney. Kyle Koppenbach. You sent me. Nice. So, what is the solution to 9 to the x equals 27? Anyone want that talk through it all? Yeah. We'll talk through it. So, let's think about the ingredients, and we'll do something similar to what happened up here. Oops, you couldn't see that. Between 9 and 27, are those both powers of a single number? What number are you thinking of? What's their common base? 3, because 9 is 3 squared, 27 is 3 cubed. So let's use that. So 9 is 3 squared, so we can rewrite that as 3 squared to the x is equal to 3 cubed. But 3 to the 2 to the x, we have a rule for that. That's 3 to the 2x. Is equal to 3 to the power 3. Now we're in business. 3 to the x is also an injective function, as we'll see on the next page. So that means the only way 3 to the this is equal to 3 to the that is if this is equal to that. So those two things in the exponents have to be the same. And if 2 times x is equal to 3, then what is x? 3 halves? Did that make some sense? Mm-hmm. Good. So, well, how about this? What if I asked you to solve 5 to the x is equal to 7? Does that look like we could use this strategy? It's not really a common base between 5 and 7. They aren't even common factors. So what we'll develop next time is, well, next time being actually kind of distant in the future, I think like a week from today, because there's no class on Friday in this class, and then there's a review day for the midterm, and then there's a midterm. So Wednesday. We'll develop the logarithm, which will let us solve things like 5 to the x is equal to 7. So the last major thing that I want to do today, the last page is, if you like, a sales pitch for an extra credit for today, is let's think about graphs of exponential functions. So we've already sketched a graph of 2 to the x, and there it was. It looked something like that. Let's try to sketch the graph of 1/2 to the x using that information. And here's what I'll use. 1/2 to the x, that's the same thing as 2 to the negative x. That's exactly what 2 to a negative power means. But how does the graph change when you stick a negative sign in front of the x? Flips over the y-axis. All of the x values become negative what they used to be. So as you can sketch the graph of 1/2 to the x, we'll take exactly the graph of 2 to the x, and we'll flip it over the y-axis. Nice. So there's the graph of 2 to the x. There's the graph of 1/2 to the x. Let's just get this out of the way. What's 1 to the x? Let's just evaluate at some points. What's 1 to the power 0? 1. What's 1 to the power 1? 1. What's 1 to the power 2? 1. What's 1 to the power negative 17? 1. What's 1 to the 1,000th power? 1. What's 1 to the x for any x? 4. No matter how many times you multiply 1 by itself, it's always 1. There's a wonderful charming XKCD about powers of 1. So let's now think about this for absolutely any valid base. So I'm allowed to take exponentials where the base is any positive number. And I think there will be two different looking cases, well, three. When b is equal to 1, well, we already know what 1 to the x is equal to. What's 1 to the x always equal to? 1. So when b is 1, there's 1 to the x. It's always 1. Let's try to sketch a graph of b to the x where b is some number that's bigger than 1. What's b to the power 0? 1, no matter what b is. So nice, that point at 0, 1 is even kind of handy. What is b to the power 1? B. And if you don't know what b is, which we don't, we can't do any better than that. But is b bigger than 1 or less than 1 right now? Bigger than 1, right? So should at 1, is the y value above or below y equals 1? Above. And without knowing more information than that, I can't do any better. 1 comma b. When x is equal to 2, what is b to the x? Well, b squared, I guess. Is b squared bigger than b or less than b? Bigger than b. At 3, you'll get b cubed, and so on. What should happen when I start taking b and raising it to negative powers? It'll get like close to 0 instead of close to infinity. At negative 1, you get 1 over b. At negative 2, you get 1 over b squared, 1 over b cubed, and so on. So there's the graph of y equals b to the x when b is positive, when b is bigger than 1. When b is between 0 and 1, let's try to think through the same thing. If you take a number that's less than 1, say 3/4, what's 3/4 raised to the 0th power? 1. Anything raised to the 0 is 1. What's 3/4 raised to the first power? 3/4, which is slightly less than 1. What's 3/4 to the second power? Well, it's 9/16, but I don't care about that really. It's slightly less than 3/4. When you take an exponential with a base that's between 0 and 1, it behaves like this. Let's see if we notice any properties of these functions. Let's check domains. What are the domains? What is the domain of b to the x by looking at these graphs? All real numbers. Whichever way you'd rather write it. What is the range of b to the x? Don't look at the case that b is equal to 1. Everything bigger than 0. What about b to the 1? What y values do you see on the graph of b to the 1? No, damn it, Chris. 1 to the x. What's the range of 1 to the x? 1. Yeah, just the number 1. Let's look at the graph of b to the x when b is not equal to 1, because the case of 1 to the x is like silly. Why are you thinking about 1 to the x? It's just 1. Just think about 1. But let's think about horizontal asymptotes. Does this graph have a horizontal asymptote? Yeah, it gets really close to the line y equals 0. Similarly, what about this? Does that have a horizontal asymptote at y equals 0? But those horizontal asymptotes look kind of different from rational function horizontal asymptotes, right? Rational functions like have the same horizontal asymptote over there as over there. Exponential functions don't. Exponential functions have one-sided horizontal asymptotes. Any questions about just graphical things involving rational functions? Oh, maybe I'll check one more thing. Rational functions, so look at those graphs. Are those graphs of one-to-one functions? They pass the horizontal line test. And maybe I'll say one more thing. What do you know about one-to-one functions?
They're inverses.
They have inverses. And those inverses are called logarithms. So let's do one last thing. Let's talk about rates of change. And if you like, this is a good opportunity to also remember what average rate of change means. So let's pick some arbitrary x value. Let's find the average rate of change of the function 2 to the x from x to x plus 1. What's the definition of average rate of change? Change in the y's divided by change in the x's. Cool. So that means that the average rate of change well, that should be 2 to the x plus 1 minus 2 to the x divided by x plus 1 minus x. Fair enough. And let's just try to simplify that down and see what happens. What is the denominator of this fraction equal to? Is 1. Just 1. That's right. X plus 1 minus x is 1. Let's look at that numerator now. I don't see anything to cancel, so anything silly like that. But maybe I do see one thing. Between 2 to the x plus 1 and 2 to the x, are there any common factors?
Well, the 2 equals 0.
So it's not like you can say 2 minus 2 is 0, because they're 2's with exponents. So you can't just subtract them. But one thing you can say about 2 to the x plus 1, what do I know about what happens when you see a sum of two things in an exponent? Yeah, it's 2 to the x times 2 to the 1. 2 to the 1 is just 2. So this will be, focusing on that, there will be a 2 to the x times 2 to the 1, which maybe you know is just 2, minus 2 to the x. Oh, that shouldn't be blue. Now do you see anything that you can factor out of the numerator? 2 to the x. So you'll be left with 2 to the x times 2 minus 1. And I'll not bother dividing by 1 because who cares about that? No, I'll put the divide by 1. Division by 1 doesn't change anything, but maybe I'll leave it there for now anyway. What does that simplify to? Just 2 to the x. Oh, so that's kind of cool. The average rate of change of 2 to the x over an interval of length 1 is exactly 2 to the x. 2 to the x is its own average rate of change. So, not having enough time, here's what I'll encourage you guys to do. So, do you think that I'll get exactly 2 to the x back even if I take average rates of change over smaller intervals? It's not clear, right? But you could go and check. You could go and check the average rate of change of 2 to the x from some arbitrary x to x plus any number h. And you could do the algebra, the same algebra, to figure out what you would wind up with. And one thing that you'll find is the average rate of change of 2 to the x won't be 2 to the x anymore, but it'll be some number times 2 to the x. There's the real definition of an exponential function. An exponential function is any function which grows or decays proportional to how big it is. Oh, I want to play home today, don't I? If you're in a big rush, then you can hand it to me as you're on your way out the door. Otherwise, you can pass it into me, and I'll walk through it. Awesome, thank you. Thank you. My office hours today are 2 to 3, right? Timing I'll be there from 2 to 3. Excellent. Good job.
Have a nice weekend.
You too.
Have a good weekend.
You too. Thanks.
I realized I forgot my math homework on upper campus.
Okay.
Can I just give it to you later today when I break between 11:50 and 1?
I may or may not be in my office during that time because I like to eat.
Yeah?
If I'm not in my office, you can slip it under my door.
Okay.
Shoot me an email when you do that.
Okay, I forgot. I got here and I'm like, oh crap, I forgot my math.
It happens.
Okay. Sorry.
No, you're good. As long as it doesn't happen like all the time, you're fine.
It won't. That was nice.
Oh. Thank you.
I do.
I was like, and I was like, no, I just don't want to do it. I shall
did it at 3.6, but I honestly did it at 3.5. It was supposed to be 17. Same type of
Sure. So here's what I think the best option is. So I mean, you can. I'm not sure which problems I'll tell the grader to grade yet. I don't decide just tell. If you turn in what you have and that happens to be one of the ones that I want the grader to grade, you won't have it. Alternately, if you can get it to me by like 3, then I'll get it to the grader anyway. So if you want to take some time to correct your homework so that it has the right problems done, you can go ahead and by the time I know this next. Yeah, and I should be in my office. If I'm not, then I'm okay with you slipping it under my door and sending you an email. Yeah.
That's why I just didn't hear anything else on that sheet.
Are they fuzzy? Sorry. I feel like I look the same. So she's like, okay, check time for a shower and make a phone. We already asked Bella.
I was in a rush at the end.
Yeah, right.
Stop judging me.
And let's see. I have homework to give back to you, and I'll give that back to you soon. You have homework to give to me. So if you want to put this one in the middle, then I'll collect it. One small people have a
This morning, I was like, make sure to turn off all the lights and make sure to go back. And I'm like, this is more now.